our study of hydrocarbons to date have focused primarily on the fact that the longer ones are less useful and the shorter ones are more useful. And therefore, when we talk about useful, we talk about the use of a hydrocarbon as a fuel. Okay, so you have your methane and you have your ethane and you have your propane and butane. Those four alone are used very, very regular and very widespread around the world as fuels. Methane is what we use in our own homes to heat and to cook with. Propane and butane would be canisters of gas that people would carry with them, or large canisters that they would put at the end of a mobile home or a caravan, and again used to heat and to cook with. So the main idea behind the short useful hydrocarbons is to see their value as a fuel. There is one way to measure the value of a fuel, and that is by looking at what we call its octane number. Okay, now octane itself is something you should all understand. Octane is a molecule with 8 singly bonded carbons. Now, that's where the name comes from. And the octane that comes from the fractional distillation column that we looked at in the previous lesson, the octane is what we call the petrol fraction. Okay, so when you have a branch or a chain of hydrocarbons of 8 carbons in length and singly bonded together, that is the petrol fraction. So what we do with that then is we play chemistry with it. We can change it slightly. We can add things to it. We can take things away, depending on exactly what we want our petrol to do. So what is the octane number? Well, the octane number is a measurement of how efficient our fuel is. Okay, and the higher your score, the more efficient you become. That's not the definition that I wanted to give back in an exam. The definition for octane number is slightly longer and a little bit more detailed, and we'll talk about that in a moment. So sometimes when you pull into petrol stations, you might see on either the petrol pump or maybe on a poster displayed somewhere the name high octane 98 or unleaded 95. Now the score here, the 98 that you see here and the 95, that's the octane number. So therefore what we could see straight away is that the high octane has a higher octane number obviously than the unleaded does, which means it's a far more efficient fuel and a better fuel for your engine than the unleaded 95 would be. Not by much, but still by 3 marks up that particular octane number scale. Okay, so the higher the number, the more efficient the fuel. Now also, you'll notice if you go into the petrol stations that fuels have different prices. So you might notice that diesel has the lowest price, and it's followed by petrol, unleaded petrol, and then there's other things in there with different mixes and different types of fuels for different, I suppose, lorries and heavier engines that have different prices attached. That's because of the chemistry we do to the octane. All right, there is chemistry behind the octane as well. It's not just that we put octane into your engine and allow that to burn. We have to do something with it because petrol during winter time has a slightly different composition to petrol at summertime, for a reason I'll talk about later on. So there's where the name comes from. Okay, octane is the long chain of 8 singly bonded carbons, and that is our petrol fraction. So when you go to the petrol station the next time and you see any reference to octane 98 or unleaded 95, now you'll know exactly what that number stands for. It stands for the efficiency. It's a measure of efficiency of that particular fuel. So where does this fuel get burned? So when we put the fuel into the car, most of us basically see the fuel going in by a pump into the side of the car. It goes into a tank, but what happens to it then? How does it transfer from being that liquid fuel into powering the engine of the car? And the answer is through what we call the internal 4-stroke combustion engine. Okay, that sounds quite a mouthful. Internal 4-stroke combustion engine, meaning that one complete cycle has 4 parts. Okay, now I want you to keep that in mind. So one complete cycle of the engine, that's one cycle. It has 4 parts to it. All right, and those 4 parts are down here. You can press on this link down here when I give you the slides, and you can see the link for yourself. But I have it opened up here already, and I'm just going to go through it with you. Okay, so there's the 4-stroke engine. Now, I want you to see how one complete cycle is made up of 4 different strokes. One, 2, 3, and 4. See that? Now, fuel and air in, fuel and air compressed, fuel and air burnt and expands, and then the waste gases are sent out through the exhaust system. So there's 4 stages to this thing. Let's start it again in a moment. Here we go. Okay, fuel and air in, fuel and air compressed, the spark plug ignites, expansion happens, the pistons push downwards, and the waste gases are expelled. Now, where does the energy come into all of this? The energy comes in now, watch, there. And when the gas is ignited by the spark plug, obviously it heats up, and when things get heated very, very quickly, they expand rapidly. So when the piston compresses the gas upwards and the spark plug fires and ignites the gas, we get a rapid expansion, which pushes the piston down and turns the shaft at the bottom, which is linked directly to the wheels. Okay, so this little shaft you see turning at the bottom, that will then transfer its kinetic energy to the wheels of the car, and off we go. So what you get: 1, air and fuel in, air and fuel compressed, air and fuel ignited, expansion happens, and then the waste gases are sent out through the exhaust system. So that's how it works, and you can look at that now in your own time. You can go through it again and see exactly how that works. Okay, so we have it there. Number 1, the piston moves downwards. Now, why does the piston move down? As the piston moves downwards, the air and the petrol mix are taking in, and you'll know why it has to be a petrol air mix. Air contains oxygen, and oxygen is needed for combustion. Okay, so if you took in petrol by itself, it would be of absolutely no value. You need to have the gas of combustion in there, which is oxygen, and making sure that the pair mix in the correct ratio so that you get perfect ignition at the right time. Then what happens? Well, the piston moves up and it compresses the gas. Don't forget, gases are the only state of matter that we can actually compress out of the 3 that we study. Okay, solids and liquids can't compress them. Gases we can. So when the piston moves up, it compresses the gas into a smaller volume, and then when the piston reaches the top of its chamber, the little spark plug will fire, and it will ignite the petrol, causing it to expand and pushing it downwards. Okay, and once it explodes, that chemical reaction then produces 2 things. It produces heat and it produces waste gases. So when it fires and expands, the piston is pushed downwards, but the chamber now is filled with exhaust gas. So the piston moves back up again in order to dispel the exhaust back out through the second trap that is on the right hand side of the actual engine, or the 4-stroke cylinder itself. Okay, so one more time: piston moves down, petrol and air moves in. Piston moves up, compresses the gas, the spark plug fires and ignites the gas. When it explodes, it expands, pushing the piston downwards, which in turn will send kinetic energy to the wheels. And then lastly, as we said already, the piston will move back up again to dispel the waste gases and to get ready to take in some more petrol and air, so the whole thing can happen again. Now this happens many cycles a minute. Okay, this happens really quickly in the engine, so that's why it's called 4-stroke, because one complete cycle is made up of 4 different stages, and we do have to know these stages, and you do have to learn them off. Okay, there are phenomena that happen with certain fuels that would be less efficient than others. Okay, and I'm just going to go through the 4-stroke process again. What can happen is the piston can move downwards and fill the chamber with the petrol air mix. But as the cylinder moves up, as the piston moves up again, something can happen whereby the petrol can ignite before it's supposed to ignite. So as the piston is on its way up and as the gas is being compressed, sometimes in fuels with a very low octane number, we get self-explosion, which means that it self-ignites. Okay, and if the petrol ignites as the piston is moving upwards, it causes the piston to shudder, because the piston is trying to move up and it's being pushed down by a gas that has ignited at the wrong time. So we get this kind of a noise, like a knocking noise. So you'll hear from your engine little noises like that, which means that the petrol is firing at the wrong time. It's not firing when the cylinder is perfectly straight and up at the top of that cylinder. It's firing as the piston is moving upwards, and it's auto-igniting. Auto-ignite means automatic ignition. It's actually catching fire by itself. It's not waiting for the spark plug. Now, as we said, petrol that does that has a low octane number. So one of the big things that chemists have to do is to make sure that this phenomenon of auto-ignition is eliminated. All right. this phenomenon of knocking, and that's what they call it. So if you can hear that sound coming from your engine, what it means is that the gas is igniting too early. And as the piston is trying to move back up that chamber, it's being met by a gas that has ignited too quickly and is trying to push it downwards. So the whole phenomenon here is what we call knocking. So what does a chemist have to do? Produce a fuel that is able to resist knocking. Or put it another way, produce a fuel that is able to resist auto-ignition, that it will ignite at just the right time when the spark plug dictates that it should ignite. Okay, so knocking is the phenomena whereby a petrol auto-ignites at the wrong time, causing the piston inside the cylinder to vibrate, knocking off the sides of the actual chamber itself and causing an audible sound of knocking in the engine. The smooth running of an engine depends on the petrol air exploding at the right time. If the air mix explodes before the spark plug fires, the piston will vibrate. And this vibration is what we call knocking. Now, it's a physical phenomenon. You can hear it, okay? When there's a problem, you often hear people saying sometimes, oh, I have to get the engine tuned. There's a reason. That they're hearing a noise coming from the engine that doesn't sound healthy. And where there's noise, there's friction. And where there's friction, there's wear away. There's damage, okay? So you can actually damage your engine. If you leave this knocking going for too long, you can damage the inside of the cylinders that hold the pistons. And that's not good. So therefore, at all times, we have to be able to eliminate as much as possible the phenomenon of knocking. Knocking causes noise, loss of power to the engine, and then eventually, as we said already, engine damage. So that's the three reasons why we don't want to be having knocking coming from our engines. First of all, it's noisy, so you can hear it. Secondly, it gives a loss of power. So the engine is not as efficient in transferring power from the petrol air mix to the wheel itself. And because there is knocking going on, there's friction going on. Okay, and where there's knocking and vibration and friction, you're going to get things wearing away and things getting damaged. Okay, so the early exploding of the petrol air mix is what we call auto-ignition. And auto-ignition is caused by, number one, long straight-chained alkanes. So octane itself would actually be a very bad source of petrol because it's too long. And the longer the chain, the more inclined to auto-ignition it is. And the more inclined to auto-ignition it is, the more chance we're going to have that if we put this thing into our engine, we're going to get knocking. Okay? It's also caused by inefficient fuel. Now, I'll talk more about that in a few moments, but there is a thing that is inefficient fuel, maybe the wrong mix, or maybe the wrong amount of air getting in, or whatever. But how do we solve it? We solve it in one of three ways, and we solve it using chemistry. Because the problem is with the fuel, okay? So as far as we're concerned as chemists, the problem was with the octane. And we need to go back and see, what could I do to the octane to make sure that it doesn't auto-ignite, that it doesn't burn at the wrong time, that it burns at the right time and therefore eliminates the phenomenon of knocking. Well, first of all, we can shorten the chain. Do you remember the class we had on isomers? We took off methyl groups, we moved them around the chain in order to see if we could have the same number of carbons but with a different structural formula. And therefore, if you still have the same number of carbons, but you shorten the main chain and branch it, your petrol becomes far more efficient, and in fact, knocking is reduced by a huge amount. So one of the most successful things we can do to octane is we can shorten the main chain, we can branch it, or we can go to a cyclic compound. So therefore, hexane could become cyclohexane, octane could become cyclooctane. Okay, so one of those two things, take the long chain, shorten it and branch it, or cut off the terminal hydrogens and join the terminal carbons to one another to give a cyclic aliphatic compound. Don't forget that benzene's not involved here. It's an aliphatic compound still, even though we tie it end to end. Okay, so that's the first way. We could also, what we say, isomerize the molecule. Now that's what we've talked about there a moment ago. So instead of saying chop it up and tear it around, just talk about isomerization. Take the octane and isomerize the molecule. Break off bits and move them around the place and see if you get a new structure. So the octane number, therefore, here's the proper definition. The octane number of a fuel is a measure, now that's most important, it's a measure of its ability to resist knocking. So that means the higher the octane number, the less knocking we're going to experience in the engine. The higher the octane number, the more efficient the fuel. It burns at the right time. Okay, now we don't want it too high. So an octane number of 100 in a car engine would be too good. So we kind of settle on roughly 97, 98. That seems to be the best level of octane number for the engines of the normal domestic car. Pentane has an octane number of 62. Useless. It will auto-ignite way too early and cause huge damage. Okay. 2,2,4-trimethyl pentane, what you notice? 5 carbons in the main chain, 3 branches. That's a good molecule. In fact, it's so good, it has an octane number of 100. That's too high for the engine of a car. Heptane, with 7 carbons, has an octane number of 0. So you would never put this anywhere near your car engine. Okay? Way too inefficient and burns way too easily at a very wrong time in your engine. But here's the interesting thing. I want to get a fuel with an octane number of 97 or 98. So how do I do that? The answer is we take these 2 chemicals here as our reference hydrocarbons. Okay, so they're our reference hydrocarbons, and then we mix these 2 in with the petrol that we want to sell in certain ratios, and the ratio of the reference hydrocarbons is responsible for getting exactly the octane number that we require. So if we want 97 or 98, we can make petrol with octane number 97 or 98 by taking the 2 reference hydrocarbons, which are 2,2,4-trimethyl pentane and heptane. Now you do have to remember them, okay? So 2,2,4-trimethyl pentane with its octane number of 100 and heptane with its octane number of 0. Both of those are taken as the bookends. And then we use those 2 hydrocarbons in certain ratios together with petrol in order to get exactly the right octane number. So cyclohexane is 83, and yes, you could use cyclohexane again, but it's a far more difficult number to use in terms of ratios. So instead of that, we only focus on these 2, and they are the reference. Okay. Good quality petrol, as we said already, has an octane number of roughly 97 or 98. So therefore it must be created. And it must be made by taking the 2 reference hydrocarbons together with your petrol and adding them in at the correct ratio so that you get bang on 97 or 98, depending on which one you wish to sell. So how do we make petrol? Now, that's an unusual thing. How do you make petrol? Well, you make petrol by first of all drilling in the sea or on land for oil. You take out the oil, you throw it into what we call a fractional distillation column. The oil seeps through, it's heated very, very strongly, and everything except the last fraction vaporizes. So the bitumen stays as a very thick black liquid and flows out the bottom. But everything else then vaporizes. And petrol will rise to about the 2nd or 3rd top layer in the fractionating column. There, it'll drop below its boiling point and it'll fall out as a liquid and it's taken away. So it's a fraction of the fractionating column. Okay. Now, that fraction that comes away is again not very useful to people at different stages of the year. Here's a reason why. When you have your car in your driveway on the 21st of December and it has snowed and temperatures are down at -2 and -3, you want to make sure that the petrol in your car will ignite an awful lot easier than it would, say, during the summer. Okay, so during the winter time we have to add different chemicals to the petrol to make sure that even if the day is very, very cold, the petrol is still going to ignite when we turn the key in the engine. All right. During the summer, the opposite is the case. During the summer, you could have your car parked in the driveway and it could read 25, 26 degrees. Now, the last thing you want is the petrol in the engine getting so much heated by the sun outside that it auto-ignites by itself and we get an explosion in the petrol tank. We don't want that. So we add in different chemicals to make sure that the flash point or the ignition point of petrol is brought above what it would be during the winter. So therefore, winter petrol and summer petrol are actually 2 different things. We add additives to petrol in the winter time to make sure that it will ignite easier, and then during the summer time we add in additives that will make sure that it doesn't flash so quickly, that in fact it needs a little spark from the engine to get going Otherwise, the temperature outside could cause the petrol to just self-ignite, and that would be disastrous for the car and for people who own it. So in 1920s, when the cars first became a big thing, okay, Henry Ford and his lovely Model T, which brings me back to the wonderful memories of Laurel and Hardy, okay, you know, the cars that were used then, they tried to use octane on its own. And they discovered that octane on its own gave rise to the knocking in the engine of the car, all right? So what they did was, they discovered, chemically speaking, that if they added in small amounts of lead, the knocking disappeared. Now, up until the year 2000, lead was present in petrol. So all the petrol we bought between the 1920s and 2000 contained an amount of lead. Now, I hope you can see the problem. Lead is an environmentally toxic metal. All right. So if you're putting lead into petrol and you're burning in the 4-stroke engine and the exhaust fumes are being pushed out on stage 4 of that cycle, then you're dumping lead into the environment, which is not a good thing. Okay. So therefore, lead pollution became an environmental issue, and its presence in exhaust fumes poisoned the metal catalysts in the converter. Now, we'll talk about the catalytic converter later on, but just to keep in mind that lead was not good for cars. Number one, it wasn't good for the environment, that we were basically throwing lead out the exhaust into the environment. That's not good. But secondly, because of the chemistry that happens under the car to clean up the exhaust fumes to make sure that they're environmentally friendly, when the lead hit this box that does the cleaning, it destroyed the catalysts. And the catalyst couldn't clean the engine fumes anymore. So again, the engine fumes coming out the back of the car were environmentally dangerous. The use of leaded petrol was phased out in the year 2000. So from 1920 to the year 2000, petrol contained lead. Okay. Now, what did they do? They took out the lead, and then they had to go back and scratch their chins and say, okay, now the petrol is knocking again. So what do we add in? The alternatives to lead were as follows. First of all, when they took out the lead, they realised that the drop in octane number of the petrol and knocking began again. Okay, chemists had to devise ways to increase it, and there were 4 ways that were now used. So first of all, isomerization. We know what this is. Just a very quick example. If you have 1, 2, 3, 4, if you want to isomerize that, you can get 1, 2, 3, 4. Okay, that's just an example on a small hydrocarbon of MEPB of butane, and butane becomes 2-methyl propane. Good. Okay. So therefore that's isomerization. Now we're doing this with the larger molecules, and we had a class on that the last day live. We went through the isomers of octane. That's the reason why I wanted to show you, coming into octane being the petrol fraction, how there are so many isomers that are available to us, and the one that will have the greatest octane number will be the one that is the shortest with the most branches. Okay, so that's isomerization. So you take the long chain and you basically break off carbons, put them around as branches, get smaller molecules of branches in order to make sure that the octane number rises slightly. Secondly, we can undergo what's called catalytic cracking. Now, catalytic cracking means that you take your octane, okay, and you can actually get a catalyst to break this chain at a very definite area. So say, for example, the catalyst comes in and breaks it here, okay? Now, what happens is the catalyst will work here and it'll break this bond, and both of the electrons that are holding these carbons together, both of them will jump ship, and what they will do is they will both go into either side of this particular original chain, and what you end up with is 1, 2, 3 with a double bond, and then 1, 2, 3, 4, 5 with single bonds. So in other words, one of the bonds here, it flips back and it joins the bond before it, or it can flip forward and join the bond in front of that. But the one thing I do want you to remember is this: catalytic cracking always gives rise to alkenes and alkanes. Now that's important, okay? So if you have an alkane and you catalytically crack it, it'll break it up into 2 smaller chains or more, doesn't matter, wherever you break them. One of the molecules, new molecules, will be an alkene, and the other one will be an alkane. Now obviously, if the catalyst breaks the chain into 3, well then 2 of those will be alkenes and 1 will be an alkane. All right, so just keep in mind the catalyst is very, very specific in nature. It knows exactly where to break this chain in order to produce the molecules of required length, and the result is that you will have an alkane and an alkene, because the electrons can't just disappear, they have to go somewhere, so they basically fold back into either the carbon-carbon bond before the break or the carbon-carbon bond after the break. Okay. What's the third thing we can do? The third thing we can do is we can reform the long-chained hydrocarbon, or what we call dehydrocyclize the long chain. Now I hope that makes sense to you. Dehydro means remove the hydrogen. Cyclization, turn it into a cyclic molecule. And let's just take again 1, 2, 3, 4, 5, 6. Okay, now that's hexane, just to demonstrate on hexane. That's hexane with all its hydrogens. Okay, what does dehydrocyclization mean? Dehydrocyclization means that first of all we remove the terminal hydrogens. So that one and that one. Okay, that's the dehydro part done. Now, what does cyclization do? It ties this terminal carbon, it ties this terminal carbon to this one, giving you carbon, 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 and carbon. So it gives you cyclohexane, which is still an aliphatic compound. This is not aromatic. So this one here is cyclohexane. Okay, so that's what dehydrocyclization means. The dehydro part is removing the hydrogens. The cyclize part is putting it into a cyclical structure, which is still aliphatic, although it's cyclic. So all you've got to remember is, if you're going to dehydrocyclize octane, what do you get? Cyclooctane. If you're going to dehydrocyclize hexane, cyclohexane. If you're going to dehydrocyclize heptane, cycloheptane. So wherever dehydrocyclization comes in, you just put the word cyclo before the original molecule, and that's the new isomer of that particular molecule. Okay, now we can't really say it's an isomer because we're losing hydrogens, but it's a new structure. It's cyclic, and cyclic structures have higher octane numbers, so in chemistry it works in order to prevent knocking. So isomerization, take it, break them off, move them around, get new structural formulas. Catalytic cracking, get a catalyst to cut the chain at specific areas, forming an alkene and an alkane. Dehydrocyclization, remove the terminal hydrogens, tie it end to end, you get a cyclic aliphatic compound. And lastly, you can add oxygenates. Now, adding an oxygenate simply means that it contains oxygen. And the ones that are most important are MTPB and alcohols. Okay, so those two, particularly the alcohols. The alcohols are good, and I don't know if you can remember back, but there was a phase in Ireland when you'd go into a petrol station and you'd see written up, now with 5% ethanol. Okay, the ethanol is C2H5OH. So it's an oxygenate because it contains oxygen. Okay, so MTBE is the other one, which can also be used as an oxygenate. But anything that contains oxygen atoms, when it's added to petrol, brings the octane number up and makes it more efficient. Okay, so there's the 4 ways that we increase the octane number. Okay, so isomerization, catalytic cracking, dehydrocyclization, and adding oxygenates. So again, make sure you understand these 4 terms, but they will bring the octane number from something quite low and miserable up to something quite high and useful. So keep those 4 ideas, and that's what chemists now do with petrol fractions. They isomerize them, or they catalytically crack them, or they dehydrocyclize them, or they add oxygenates to them. Okay, so we know already what isomerization is. It's taking a long, less useful hydrocarbon and turning it into a shorter, branched, more useful hydrocarbon. And we've had this already. So just for example, there's 1, 2, 3, 4, there's pentane. Pentane with an octane number of 62 can become, you name that one before I say it. Good. 2-methylbutane, which has an octane number of 93. Okay, so even just moving one little methyl group around the place changes the octane number from 62 in the straight chain to 93 in the shorter branched chain. Okay, catalytic cracking, as we said already, is where we take a catalyst, in this case here, a mixture of aluminium oxide and silicon dioxide. By the way, silicon dioxide is just sand. We'll talk more about that later. So aluminium oxide and silicon dioxide at a temperature 500 degrees. Look what happens. The C20, useless, C20 is so long that it's actually a waxy solid, a waxy liquid, okay? Kind of a waxy, solidy liquid. It's kind of in that phase, but it's useless. So what does this catalyst do here at this high temperature? It takes the C20 and it chops it up into two C10s. Now, here's the thing. So let's say, for example, 1, 2, 3, 4, 5, 6. Let's just say this way. It chops it in the middle, okay? So the catalyst attacks in the middle, causing that bond there to be eliminated and to jump either forwards or backwards. So let's just put it here, into the two carbons before the break or the two carbons after. So that's why you get an alkane and an alkene. So just keep that in mind. When we catalytically crack, we will always get alkenes and alkanes in our mixture, and they will be formed exactly where the break is made by the catalyst. Okay, it's carried out in the lab using paraffin and porcelain. Now again, this is something we can't do this year, but we will do as soon as we get back in September, and I'll show you how it works. But you'll be able to then test for various different saturated hydrocarbons and unsaturated hydrocarbons. And I hope you remember the test. When we give you paraffin and we then crack it and we collect the gases, we will add in one of two things, either bromine water, which is yellow, or we will add in acidified potassium permanganate, which is purple. Now, both of those, if you mix them with the results of cracking, will lose their colours. What does that tell you? The results of cracking contain unsaturated hydrocarbons. They contain alkenes or alkynes. All right, now we know it's an alkene. So therefore, we need to test it just to make sure that there are new alkenes present. Use yellow bromine water or purple acidified potassium permanganate, shake it with the resultant gases, and the colours should disappear. Okay, so that's what we're going to do when we go back in September. Do you notice it's very, very similar to the experiment we had for making ethene gas? You have your glass wool, but this time you have your liquid paraffin. Okay, you have here porcelain pieces, which are pieces of actually very hard material. They'll act as the catalyst. You heat the catalyst to a very high temperature, and then we get this thing will vaporize, and it moves over the catalyst, and as it moves over the catalyst breaks the chain. And paraffin is a long chain. So it breaks the chain, and the chains then that come out here are far smaller. You will have alkanes and you'll have alkenes in the mix. So yes, there'll be alkanes, and there'll also be alkenes in the mix. And we can test that mix up there then with bromine water or with acidified potassium permanganate to show that both are decolorized, meaning yes, I made alkenes through catalytic cracking. So very, very similar to the setup that we used for the production of ethene. The same procedure, same apparatus, just the only difference is we're using paraffin and porcelain pieces to crack the long chain into smaller, more useful hydrocarbons. Okay, dehydrocyclisation, as I told you already, will involve again a catalyst which will remove the two terminal hydrogens and put them together as H2, hydrogen gas, which will be collected as a gas. And then it'll tie the two terminal carbons to one another to give you something like this. Okay, so there's N-heptane, 1, 2, 3, 4, 5, 6, 7. So this is heptane. And what happens here in one particular process is we can turn heptane into toluene. The toluene is better known as methyl benzene. And we'll come across that later. So we can take heptane and turn it to methyl benzene. And that there would now be an aromatic hydrocarbon. Okay, and notice we get 4 molecules of hydrogen given off. Now, is that a waste product? No. This hydrogen on here will then be sent off as a fuel. And I'm going to talk about hydrogen on its own in a later lesson. Okay, so that hydrogen will be sent away as a fuel in order to be sold, bottled and sold. So there is money to be made on this process as well. Dehydrocyclisation, we said, involves the formation of benzene, but there's a problem. Benzene is carcinogenic, okay? And therefore we don't want to get benzene by itself, but methyl benzene is fine, or ethyl benzene is okay. So we do have a process by which we can use dehydrocyclisation to turn an alkane into a cycloalkane, so heptane into cycloheptane, and then we can further work on the cycloheptane to give us methyl benzene. Okay, so keep that in mind. Therefore, petrol contains 3% benzene. So there will be aromatics in your petrol. Now, think about that for a moment. 1920, Cars arrived, petrol put in, knocking occurred. Petrol had lead added to it, knocking disappeared. Lead was used from 1920 to 2000. Lead is now an environmental poison. Okay, it's a toxic metal, so we can't use it. So we take it out. But what do we replace? Benzene. Benzene is carcinogenic. So there'll always be a layer of danger with petrol because of the various different compounds that are within there. So petrol will contain 3% benzene, which is carcinogenic, and today is still a cause of concern. So petrol, the lead in petrol used to be the cause of concern. Now the cause of concern going forward into the future is this 3% benzene that is in there. Okay, but it's there, it's in all petrol, and it is a cause for concern. And it'll be interesting to see that when they take the benzene out, what did they replace that with? Okay, and lastly then, as we said, adding oxygenates. And oxygenates are any molecules that contain contain oxygen atoms. Okay, any molecules that contain oxygen atoms. The most widely used oxygenates are alcohols, because all alcohols have an OH group. So all alcohols will have oxygen atoms present within them. Okay, the other one, which you do have to learn, is MTBE. Methyl tertiary butyl ether. Now just learn the name, because they can ask you in one of the questions, particularly question 4 in the exam, what do the letters MTBE stand for? Methyl tertiary butyl ether, which is very rich in oxygen atoms, and therefore is a very good oxygenate compound to add to petrol in order to bring up the octane number. Their presence in petrol increases the octane number and gives rise to very little pollution. Why? Because when you burn oxygenates, you only get carbon dioxide and water, which are two relatively harmless gases. So they're fine to add to petrol. Benzene, don't know. Oxygenates would be a far safer way to go with rising the octane number of a fuel up to a very efficient level. Okay, so therefore, just to finish this, as we should now understand, petrol itself is a very complex mix. Okay, the petrol that comes out of the distillation column, as I said already, is not the petrol you're going to put into your car. It needs to be worked on. The octane number needs to be brought up by one of 4 things: isomerization, catalytic cracking, dehydrocyclisation, or the addition of oxygenates. So when the petrol comes out of the fractionating column, it's brought to the lab and it's worked on. Also, petrol that we buy in winter time has to be different from the petrol we buy in the summertime. So therefore the chemical composition of petrol is continuously changing as the seasons change, to make sure that the petrol can still be used irrespective of whether it's surrounded by a very cold temperature in the winter or a very high temperature during the summer. All right, so do we get petrol from crude oil? Yes. Is the petrol from crude oil what we put into our cars? No. We have chemistry to do on it, and the chemistry that we do on it then to make sure that the petrol that you get into your car 365 days a year will have a perfectly acceptable octane number and will ignite exactly when you require it to. Okay, so I'm going to leave it there. I want you to review those slides. I am going to send out a few questions in relation to petrol, which I will ask you to do and have ready for the next class, and then we'll review those questions and we'll make sure then we can move into hydrogen. I want to focus in the next class just on hydrogen itself as a source of a fuel.